All right, I'd like to do another example of what Osgood calls in the notes duality properties, but this time in the discrete time domain. So duality for discrete time signals. And this is, for instance, by duality properties, you mean things like Fourier transform of f minus equals Fourier transform of f minus. It's just sort of the duality, meaning it's the interplay between various different operators. So here, of course, we're talking about the Fourier transform operator and the minus operator on functions. And then how do they interact? If you apply the minus first to the function or later to the whole thing, well, it looks like you get the same thing. So let's check this out in this case of a discrete time signal. So if f of t is discrete time, then of course we define the Fourier transform of f as a function of omega, and that's just the sum, the infinite sum, t equals minus infinity to infinity, and then f of t e to the minus I omega t. And omega is going between minus pi and pi. And then if g of omega is continuous on minus pi to pi, then we can say the inverse Fourier transform of g. This inverse Fourier transform is then a function of t. This is the reconstruction of a signal, right? And so that's just going to be, sorry, not the sum, but the integral, and we take 1 over 2 pi, then the integral minus pi to pi, g of omega, the frequency content, and then e to the I omega t, d omega. All right, so let's investigate what happens if I take the Fourier transform of a function f minus, where again the minus operator is just applying to f, and then I'm taking the Fourier transform of that whole thing. That whole thing then is a function of omega, all right? And let's just write this out. So we would get the summation t equals minus infinity to infinity. F of minus t goes in here because these are the function values of the signal f minus, right, the reverse signal. And then I've got e to the minus I omega t, forward Fourier transform. So that looks like the signal, or the summation, t equals minus infinity to infinity. And then I can put f of minus t here and just make one slight change, e to the I omega and then minus t. Now, if you stare at that for a minute, right, what is this doing? It's pairing f of something with e to the I omega of that same something here, okay? Whether I call this minus t, or I call it u, or I call it t, it doesn't matter. If I pair this up and add all the way from minus infinity to plus infinity, I would get exactly the same sum. In fact, if I just change that to a plus t. Okay? Now, what this is not saying is it's not claiming that if t is equal, if I take minus t, where t is equal to 5, let's say, then I've got f of minus 5, e to the I omega minus 5, right? It's not saying that I will get the same value when I take t equals 5 over here, right? But what it is saying, of course, is that that same term in this infinite sum will occur on this side when t is minus 5, on this side when t is 5, which is really pretty obvious or easy to see, right? The one point about this is you cannot get away with reordering a sum like this if, in fact, the sum doesn't converge, right? Then you could get really crazy values on one side or the other where some of the partial sums are converging here and they're not converging there, depending on which direction you're going. So in any case, here it's perfectly symmetric and we get this as the result. So now let's just check what happens when we take, on the other hand, when we take Fourier transform of f and we do the minus operator on the Fourier transform, on the whole Fourier transform, we do the minus operator and then we evaluate that at omega, right? So how does this look? Well, first of all, this is Fourier transform of f, and then evaluated at minus omega. All right, so now, again, we get the summation t equals minus infinity to infinity. And we've got f of t here, because I'm taking the Fourier transform of f, right? Then I get e to the minus I, but this is a function of minus omega now, so I just stick in the minus omega here. And we're basically there, right? You can see already that this is just equal to the same thing. I just get a cancellation of the minus. Okay. And so these two then just tell us that indeed the same thing happens. I get Fourier transform of f minus is equal to the Fourier transform of f minus. Just written purely with no variables in this form. It now just looks exactly like the one we did for the infinite domain or signal processing world number 4. The formula is now identical, right? It's just in a different set of domains. Let's also do it for f minus, or sorry, f inverse. Let's just at least start that and see how that goes. So, for instance, in this case now, I would want to take f inverse of g minus, right? And then I'm thinking of g as a function of omega, right? G minus is also a function of omega. And so then this would be now the inverse transform would be a function of t. And I would get this by doing 1 over 2 pi times the integral minus pi to pi, g of minus omega. Okay, so we take the g minus function as giving us all of the frequency components. That means just take g of minus omega. Then I've got just the positive exponential, e to the I omega t, and then d omega. This gives me my function of t, right, which reconstructs that signal. Okay. Now, in this kind of case where you're stuck with a minus inside of the argument of a function, and there isn't any other trick you can get to either have it cancel out, or in this case to have it pair up with a minus somewhere else. In this case, what we need to do is just do a u substitution in the integral. So if I go with u equals minus omega, and du, then it's just equal to minus d omega. Right? Then this integral can just be rewritten. Now, one thing you have to be careful of is the limits of integration will swap as well, right? So when omega is equal to minus pi, u is plus pi, and when omega is pi, then u is minus pi. So the integral now goes from pi to minus pi. I can flip that and get another minus sign. But let's just first of all write it that way to keep track of it. And then here I've got g of u, and then I've got e to the minus I u t, right? Because I had an omega here, that becomes a minus u. And then the differential becomes a minus du down here. Okay? Well, we can simplify that one step further at least, and take the minus sign out in front, swap the limits of integration back to the usual ones, which will cancel that minus sign, and so that just gives me 1 over 2 pi integral from minus pi to pi, and then g of u e to the minus I u t du. Okay, so that is the Fourier transform inverse, the inverse Fourier transform of g minus. Okay, if we just quickly do up here, what would be the inverse Fourier transform of g, and then minus operator applied to that as a function of t. Okay, well, again, inverse Fourier transform of g, and then evaluate this whole thing at minus t, right? Let's just put in the minus down as it's in the definition of the minus operator, or the reverse operator if you like. So now I've got 1 over 2 pi minus pi to pi. I've got the g function for the frequency components, because I'm doing inverse Fourier transform of g, right? And then I just have to remember to stick the minus sign up here. This would be e to the I omega and then minus t. right? And then this is d omega. All right. Well, I've got the integral, I've got 1 over 2 pi integral over omega e to the minus I omega t, and then d omega. I've got, the only difference here is the difference of labeling, right, of the variable, u, and u. Otherwise it's identical, and so of course I don't need to do any substitution then to see that indeed those two formulas they compute to exactly the same thing, even though I'm using a u here and an omega there.